Morning, everybody. Today we are going to continue the topic of the variational autoencoders and specifically look into the conditional joint and semi-supervised encoders as applied for the spectroscopy and imaging data. So first of all, let's have a sort of brief recap of this part of the course. So we looked at what are the variational autoencoders and learned a little bit about the primary notions associated with the autoencoders. So what is encoding and decoding, what is latent distribution, what is latent representation. So we had a quick look into the invariances, including rotational, translational, and scale invariance, and why they are absolutely necessary for analysis of the imaging data. And today we are going to look at the different ways that the autoencoders can be configured with respect to the labeled or partially labeled data. So first, let's kind of recap what the autoencoder is. So generally, autoencoder is the network where you have the input, so your input layer is structured in such a way as to accommodate your data, whether it is image patches or spectra. You have some form of the convolutional funnel, so it can be a convolutional network, it can be graph network, it can be the fully connected perceptron, so you choose the one that fits your data and your data format. So that ultimately channels it down to the latent layer. So the only thing that matters about the latent layer is that the number of variables here is small. Then you take these latent variables and then you deconvolute it back into the original data, or the data having the same dimensionality as the original data. So the way that you train the autoencoder is you try to minimize the difference between the input and the output data. So essentially it learns to reconstruct the data from itself. The reason why it is useful is actually because of this latent layer. So once the autoencoder is trained, it basically learns how to take the original data set and how to represent it in terms of the small number of the latent variables. So this is called encoding. And the properties of these latent variables are such that they allow us to either encode the data. So this is the example of the MNIST data sets. When we start with the 28 by 28 images, then we project it in the latent space, and then we see that different labels are distributed differently in the latent space. So this is what we do with the encoder part. The decoder part allows us to take the points in the latent space and represent them in the real space. So for the two-dimensional latent spaces, the convenient way to do it is through the so-called latent representation. We essentially create the set of rectangular grid of points in the latent space. We take each latent vector on this grid, decode it into the real space, and then we represent it as this type of image. And you can see that the latent space is divided between the individual digits. So ones, zeros, threes, fives, sevens, they all found their place in the latent space. So the reason why autoencoders are exciting is because we can generate the new digits. So if you look at the original data set, you can see that we have a lot of points, but there are parts of the latent space that are free. However, we can decode the images even from this empty parts of the latent space. So in this way, we can create the new in-distribution data. So by definition, this is the generative distribution we generate from. Sometimes this digit will make sense. So if we interpolate between two ones, it would be another one. Sometimes these digits will not make sense. So if we interpolate between the 0 and 1, that would be something unphysical, as you can see here. So the third thing which we really care about the autoencoders is their capability to disentangle the representations of the data. So this is something that is exceptionally important, and I believe we are just scratching the surface of what can be done with the data disentanglement in complex systems. But in physical systems, obviously, the computer science community have been exploring it by now for quite a while. But it's also something that does not have a rigorous definition, at least to my knowledge, but it's something that is also very easy to illustrate. So this is the example of the conditional autoencoder. So we are kind of jumping a little bit forward here, which basically shows that now we have a latent space for each variable. And you can see that within each latent within each latent space, there is an ordering of our characteristic traits. So all the 6s are broad on the left, all the 7s are broad on the left, and so on. Once we move from left to right, they become narrow. Once we move from top to the bottom, the direction of the tilt actually changes. So it is intuitively obvious for human eye, and it is very difficult to describe from the physical point of view. It's traits within the data. And we also looked at the invariances in the data. So this is invariant autoencoders is a fairly unusual topic. So in most problems that appear in the computer science domain, invariances are not that important. So for example, if you want to recognize handwritten digits, you basically orient the piece of paper always vertically. When we run the microscope, we have no expectation about what orientation our features of interest will have in the image space of the microscope. And therefore, they can be oriented in any way. So for each specific image, we, of course, can say, hey, we have a preferential orientation. But first of all, it's generally not true because the image can be disordered material or have multiple grains and so on and so forth. Or we generally expect to have the algorithms that are not sensitive to rotation or other invariances associated with the imaging system. So rotational autoencoders basically allow us to analyze data like this. They separate the rotation as the separate physically defined factor of variation. And this is the comparison of how the VIE and rotational invariant VIE behave for the strongly rotated Mies data set. So in this case, we have the handwritten digits, but we rotate them by very large degrees. So you can see some of them are almost horizontal, some of them would be actually upside down. So the normal VIE fails rather miserably in this case. So you can see that the rotation becomes the primary factor of variation across your latent space. RVIEs basically order them all in the same direction. So that's why they're very useful. So it turns out that for those of you who are more inclined towards the fundamental physics, there is actually a deep connection between the structure of the latent space of the autoencoder and the fundamental physics. So this is so-called the Lie groups. So the rotational autoencoder have the latent space invariant to the SO2 group. And it actually opens the pathway to explore the relationship between the autoencoders and topology and all other cool physical phenomena. So this is not very, it's not particularly useful for everyday analysis, but it's an important thing to know that once you work with the rotation invariant autoencoders as opposed to the normal one, you actually deal with something that is very deeply connected to the fundamental topological properties of the generative spaces, which is something that we normally think is not really relevant to the electron microscopy or any other science that we are likely to do. So that being said, and after repeating what the autoencoders is all about, one thing that you notice is that VIEs are a very powerful tool. They are incredibly good in disentangling the factors of variation within the data. And factor of variation is everything. So on the examples of the Mies data set, the digit is the factor of variation. The handwritten style is also a factor of variation. Of course, we don't know what these factors of variations, what is the ground truth, but what we analyze is sufficiently convincing. If we analyze the cards data set, as in the example that we went through on Friday, so in the cards data set, it is a synthetic data set. We know the ground truth factors of variation there. So one is the suit, another is the rotation, the third is translation. So we create them, we see that the autoencoder disentangle them, but they disentangle them equally. So one thing that you also noticed is that the way that the different traits of data accommodated in the latent space depends on this degree of variability. So the examples that we've seen with the cards having small distribution in angles and large distribution in angles shows that if you increase this distribution, the manifold tries to extend to accommodate this variability. So this is super good. It works. We can always play with the dimensionality of the latent space to ensure that we accommodate the intrinsic variability. So I always use the two-dimensional spaces for visualization purposes. Practically, we can choose whatever latent space you want. But you may say that not all factors of variability are equal. For example, if I'm looking at the cards data set, I kind of intrinsically understand that the suit of the card and the rotation or distortions are different factors of variability. VIE will put them all in the same latent space. So the question becomes, what can we do to adapt VIE and make them more flexible to analyze the data that has a dissimilar factors of variability? So this is exactly where the topic of this lecture comes from. So this is what is going to be conditional, semi-supervised, and joint VIEs. So of course, there are multiple other ways that you can configure the VIEs, but as follows from this course, we developed the ML tools that are suited for the problems that emerge in the context of the electron microscopy. And the typical problem that you have in electron microscopy is dealing with the multiple objects in the image. So particles of different rotations, phase mixtures, and so on and so forth. So what can we do? So the first scenario that we encounter is the scenario when the classes are somehow known. So where they're known from, it depends. So maybe we have some other way to identify them. Maybe our data is sufficiently discriminating that we can separate them. And I'll show you an example of how it works. So this would be the conditional discrete VIE. In fact, the example of the disentanglement of latent representations I have shown you is actually using the discrete conditional VIEs. So the second scenario is when the factors of variability are known, but they are continuous. So for example, it can be a single parameter that is attached to each data object. It can be actually a vector of parameters, but in some sense, it is a latent variable which is known in advance. So where these parameters come from is a guess. So this is going in the great unknown to some extent. So this factor of variability can be, for example, the temperature when you take in the experiment. It can be the beam parameters. Whether this is useful or not is something that needs to be explored and experimented with. So for the time being, I'm aware about 3 or 4 papers where the conditional VIEs have been used for the physical problems. So if you decide to go and explore this direction, you would be basically doing something new. The third example is when some of the classes are known, but not all of them. This, in fact, is a very common problem. In fact, surprisingly common. So the scenario when it appears is, imagine that you have a textbook which has an example of some image. So this is how crystal of this compound look like. This is how the crystal of that compound look like. Or another example is atlas of the biological species. This is how the pollen particle of this particular species look like. So if we have an example and then we try to look on the unfamiliar image, and classify the objects that we see there based on those examples, this would be a semi-supervised VAE. For those of you who worked with the machine learning application hands-on, it is also great because sort of all of you are probably familiar with the problem of labeling the data. That takes quite a lot of time and effort. So VAE basically allows you to, rather than creating large label data sets that you can use to train the supervised networks, you can identify the small number of the data sets and then use semi-supervised VAE in order to identify the objects of the same type within the image. So this is a very, very powerful algorithm that allows you to compare the data to the published one, the images to the published one, and it also allows you to really reduce the amount of the labeling you have to do. So the final example is the joint VAEs. So the joint VAE is simply the case when we don't know anything about the data other than that there are classes and the number of classes. And then basically we tell our algorithm to take our data set, separate it in the given number of classes, and also disentangle the representations within the class. So just to go through a few examples. So this is how the conditional VAEs look like. So this is the example. So we start with our data set as before. We have our latent variables. We have our transform that makes this autoencoder invariant. So we can choose which one we want to apply. And we apply the class conditioning. So class labels have to be provided along with the original data. So this is how it works. As all autoencoders, there are multiple layers at which you can engineer it. For example, you can modify the loss function to have some additional physical priors. And this is the examples of how they look like. So for the MNIST dataset, if you have the application of the conditional variational autoencoder, now you have the latent space for each of the digit because that's what we condition upon. So the important thing here is that it clearly allows you to see why the rotational invariances matter. So if we have no rotation, then you can see that we have a latent space for each digit, but the center of the latent space can be absolutely unphysical. So for the zeros, you can say, hey, this is just a rotational invariant zero. Maybe some people write this way. I mean, nobody writes 1 like this and nobody writes 8 like this. So, but given the fact that our average invariance, we apply the strong rotational disorder, the center of the latent space is occupied by the elements which are fully rotationally invariant. And since there are none of them, they look very unphysical. So once we have the fully rotational autoencoder, now our latent space are beautiful. So we clearly recognize the right answer. And one very important thing that appears over and over again in the context of the VAEs is that we very often judge whether the algorithm worked or not based not on what it shows, but what else is remaining. So in this case, we conclude that if our latent spaces look absolutely non-inspiring, so there is not much interesting here, you can see what the factors of variation are, but they essentially the width of the letter, so both here and here. Basically, it means that we discovered our strongest factor of variation and we already took care of it. So what remains is very little variability. So think about it that if we take a physical problem and we start to apply a set of VAEs on top of it, it's almost like taking the shells out of the onion. So we basically disentangle the complexity one layer at a time. If what we removed made the data complicated, the remainder would be simple. If what we took out is irrelevant, then our data will remain complex. So this is an example of the VAE on the card data space, on the card data set, so which is simpler than MNIST. And in addition, we know the factors of variability. So you've seen the example of this card data set on the last lecture. So this is high rotation, high shear. So we formed the independent latent space per class. So in this case, it's conditioned on the class number. So we have a single latent space per class. If you look at this latent spaces, you can figure out what it actually means, so what the latent variable means. So you can see that this latent variable represents essentially some geometric transforms. So you see how they're tilted to the left here, and this basically this becomes a shear. So you can see that this one is sort of a little bit tilted but symmetric. This one is very clearly sheared. So if you look at the remainder, you can see that all of them have the transformations which are identical between the different classes, as they should be, because when the conditional autoencoder works, it disentangles the representation of the data in the same sense between all the classes. And then, of course, since in this case we have access to the ground truth labels, you can see that how our manifolds look like and in the latent space, and what is the variation of the factors of variability across the manifold. So look what happens, that for all 4 classes, the manifold has exactly the same shape. In fact, if we superimpose them, you can see that they adopt the same configuration. So the reason why it happens is because we applied exactly the same factor of variability, meaning rotations and translations for all 4 suits of the card. So basically it tells us that not only the latent representations are comparable, but even latent distributions are almost overlapping. So it's actually pretty amazing if you think about it, because we took 4 classes of objects, we applied the same transforms, we give this object to the conditional autoencoder. Conditional autoencoder does not know what the transforms are, so we only tell it the class, but it finds a way to reorganize the data in such a way that it discovers that transforms applied across all the classes are the same. So this is really not a small thing if you think about what actually discovered. And you also see that in this particular case, our remaining factor of transformation is the shear, and you see that it changes across all the manifolds in the same sense. So it is maximal here, and then it kind of changes monotonically across the manifold. So we truly discovered the factor of transformation. If the data set did not come up with the ground truth, we would have to assign this factor of transformation ourselves. But the important thing is that it works. And interestingly, that we also found the correct angle. So if you compare the predicted angle, which is learned by the autoencoder, versus the ground truth, you can see that it's almost a straight line. So obviously, CARD is a relatively simple example. For a real data set, making it work is a little bit more complicated, and it's often not so impressive. But the sheer power of this algorithm to find the complexities in the imaging data set is really, really impressive. So what happens if we apply it for the experimental data? So the problem in the experimental data is that very often, once we have the data coming from the imaging tool, we don't know what the classes are, which basically means that we kind of need to assign these classes ourselves. So one way we can do it, for example, for the graphene data, is basically assign the classes based on the number of rings in the patch that contains roughly 3 unit cells of the graphene. So, for example, one of the notebooks, actually, I didn't put it in the GitHub, but I'll do it by the end of the day. It basically shows the example when we create the classes with fewer than 2 rings, 2 rings of 6, 6 size, like this one, the rings 5 and 6, the rings which have 6, 6, 7, 3 rings 6, 6, 6. So this is an ideal graphene. defects like this. So basically, we create the classes by enumeration of the number of rings adjacent to the central atom. There are other ways we can generate the class. So this is something that you do in order to fit the specific problem that you have. It's a sort of typical example of the feature engineering. And once you take this and put them in the autoencoder, this is how you represent the data. So as you can imagine, in this case, we will have 7 latent spaces. The way we can represent it is through the so-called transversal manifold. So transversal manifold has the discrete latent variable as the vertical axis, and the continuous latent variable as the horizontal axis. And here you can see what are the factors of variation, and again, play with this data and figure out what it means. Of course, the great thing of the imaging data is when we run this analysis, we get to generate the latent images. So normal applications of variational autoencoder don't have latent images because the data can be anything. Once we apply VAEs of any sort to the experimental data, and we take either hyperspectral data sets, or we use some form of patches generated from the large-scale imaging, we actually get to visualize it as the latent images. So what we do in this case is basically we take each carbon atom, which we find using the deep convolutional network. So you've seen the example of that. We find the patch around it. We create the class labels and the class labels manually. So by the analysis, not manually, of course, but by some unsupervised analysis. Then we send it with the classes to the VAE, and then we encode angles. We encode the latent variable Z1, and we encode the variable Z2. And then depending on how these variables are distributed, we can probably make some conclusions about what they mean. So the angle is straightforward. So angle is an angle. It basically shows you how the sp3 bonds around the, sp2 bonds around the carbon atoms are oriented. So you can see this checkerboard pattern, which kind of normal. For first latent variable, you can see that it changes continuously across our image, and it shows the clear regions of bright contrast and clear regions of the dark contrast, which basically lets us conclude that this is something related to the ordering inside the graphene lattice. So it can be strains, it can be something else. So we need, of course, to look in detail in what it means, so how this latent variable affects the geometry of our object. The good thing is that we have a clear guide to its behavior from the observational data. So the same time, the Z2, our second latent variable, it actually sort of looks like a little bit like a checkerboard as well. So this is quite normal. So it basically means that we're probably trying to deconvolute too many latent variables. So classes Z1 and the angle would be enough. There is some partial leakage between the latent variables. Again, remember that the autoencoder does not have access to the ground truth. It has to figure it out, and it can be imperfect. So once you see the phenomena like this, this is where the life becomes interesting. So you can either say that it didn't work, or you can try to start to focus on how to train the autoencoders properly and make sure that you choose the right values of the beta parameters, that you are careful with the annealing trajectory, and so on and so forth. So for the time being, most of this work is done essentially manually. So as in many cases, the tuning of the hyperparameters of the neural networks is primarily done manually first. In principle, it is possible to use the optimization tools such as Bayesian optimization in order to tune these hyperparameters. The difficulty in use of any automatic optimization tool is that you need to define the objective somehow. And it is possible in a sense that we experimented with this. For example, you can say that, you know what, my objective is to avoid the high frequency features in this image. So what I mean by that is that on this image, you can see that the contrast associated with the latent variable changes smoothly on the length scale well above the distance between the atoms. So intuitively, from physical viewpoint, it seems immediately obvious that this is right, because in this case, we deal with something that is strain field or any other physical order parameter that we, by definition, expect to change smoothly. And the sharp discontinuities can be only at the defect sites. So one way we can train the autoencoder is to put the penalty that represents the degree of rapid variation inside the image. So the simplest way to do it is to basically calculate the Fourier transform and take the intensity of everything outside of the central peak and say that this is an additional penalty function for the autoencoder. So this approach works. The great thing about the VIEs is that they can be modified to allow this type of operation. We actually have a paper of arXiv that shows that it has done, that it worked once. That may be a very interesting direction to explore in the future, because solutions become robust only if they have been followed by multiple groups multiple times. So anyway, going back to the types of the autoencoders we can work with, the next type I wanted to mention is the semi-supervised autoencoder. So what does semi-supervised autoencoder mean? Basically, it says that, look, I have the data set, I have the class labels, but I have class labels only to the small fraction of the data. So not all of them, only a small fraction. So it is kind of, in some sense, halfway between the conditional autoencoder, when you have a class label for each data object, and the normal autoencoder, or joint autoencoder, when you don't have any class labels, you just know the number of classes. So it turns out that conditional autoencoders will do two things. So with the data set, it will take each object. If the class is not known, they will provide the class label, and they will also provide the disentanglement within the class. So the great thing about the rotation invariant one, that they will, if all your examples are in vertical orientation, it will find you the examples of the figures of the same objects of the same type having the arbitrary orientation. So we are going to look at the data set that illustrates the rotationally invariant semi-supervised autoencoder, but these are just few examples for the class where, again, we have the usual latent space, we have the usual variation, and in this case we get to compare it to the ground truth, because when we block some of the labels, we can kind of compare the classification results with the true answers. So we can do it for the latent representation, and we can do the usual confusion metrics, similar to what people use for the supervised neural networks. So in this case, you can see that even for strongly distorted data set, we were able to identify most of the suits correctly. And it's kind of interesting to see what suits got mixed. So for example, you can see here that very often we interestingly mix the hearts and the clubs. So somehow this intensity is pretty high. So, and the reverse is also true. So hearts and clubs somehow get mixed together. Diamonds can be separated very clearly. They're very different from remaining three. Pikes can be separated very clearly, but these two classes get mixed quite appreciably. And again, we still have the property of the shear distribution of the disentanglement of the factors of variability, which in this example would be shear. So same approach works for the, so as I mentioned, this is really great technique when we apply it for the experimental data set, because rather than labeling all the data, training the neural network, or training the ensemble network to account for the factors of variability, we simply can label few data sets. And in fact, we can do it just during the experiment because it's fast. And then our semi-supervised autoencoder will basically assign all other observed features to the same classes. And this is the example of the same analysis for the data set of the graphene. So we label several examples of the specific defects, and then we try to identify all the other structures within the image. And in this case, since we have the full class labels, we can also analyze the confusion matrix, and you can see that it worked remarkably well. So it is easily 70–80% recognition. So the final type of the autoencoder that we want to go through is the joint autoencoder. So the joint autoencoder has a fairly complex mathematics under the hood. So they essentially appeared only 3 years ago, because it is not an easy problem to disentangle the representations within the class and separate the data in different classes. So there is a trick that allows to do that, called the Gumbel softmax trick, as there is which kind of requires the certain tuning of the autoencoder in order to get the result. But practically, this is how it works. So I've showed you the example of the MIS data set. So let's assume that we have a MIS data set and we want to separate it in the 6 classes. So 6 is obviously not the right number. Realistically, there are 10 classes. But if we give it to the autoencoder, this is what it's going to do. So again, these are transversal manifolds. This is the direction of the continuous latent variable, one of the two. This is the direction of the discrete variable. So here we have 6. So see what happens. The zeros got a full latent space for themselves. So you can see that they're sitting only in one of the 6 latent spaces. Ones took a full latent space for themselves, and 6s got a full latent space for themselves. Notice that within the latent space, there is a disentanglement of the representation. So you can see that 6s and 0s are chunky on the left and kind of narrow on the right. So same as we've seen before. Same thing happens to ones, but sort of since ones have the same widths, we cannot see that. For other variables, situation is different. So we see that 4s and 9s, and to some extent 7s, are sitting in one latent space. 8s and 3s and 2s are sort of sharing another latent space. And so 5 and 8s are also sitting in the same latent space. So what happens if we choose the right number of latent spaces? So let's say we have, that there are 10 classes. So in this case, as we can expect, 0s, 1s, and 6s are still good to go. It looks like 7s start to get their own latent spaces, but say 3s and 8s cannot be still separated, and 5s and 8s cannot be separated. So this is definitely not a right division. So the question is, what else can we do with that? So, okay, let's assume that we are going to create a very large number of classes. For example, we make 18 classes, much more than true factors of variation. So in this case, we actually start to see that zeros now kind of occupy 2 of the latent spaces. Some of them start to separate better, like 6s and 9s become more clear, even though 9s and 4s are still kind of close to each other. And you can see that now we have 2 latent spaces when there are 9s and 4s coexisting. So basically, the idea here was that maybe we can use something like agglomerative clustering when we first split everything in the large number of classes, and then we try to group them based on the similarity. Turns out that it doesn't work, at least it doesn't work easy. And the reason why it doesn't work is because the matrix that determines the difference between the classes and the variation of due to the factors of variation within each class is actually comparable. So in order to do it better, we actually need to learn how to intervene during the training process. It is technically possible, but we haven't done it before, done it to this moment. So anyway, we can also explore the individual class. So in addition to the transversal latent representation, we can have a normal latent representation. So they're very familiar. And the question becomes, can we somehow at least monitor what goes on? It turns out that one way that can be done is using the ensembles. So one thing that we observe is that if we train multiple joint out encoders at the same time, the classes that are robust, they are always the same. And the classes that are a mixture of classes, that kind of train differently. So if we train multiple autoencoders at the same time, you can see that there is a dispersion of prediction. And usually at the higher dispersion, the larger is the variability of the class. So maybe this is something that can be used down the line to make them self-learning. So again, the area that we're exploring. How would the joint autoencoders work for cards? So the great things for cards is that we create our own data sets and we can control the factors of variability. So that's the difference between the card data set and the MNIST data set. And you can see that if we are careful and tune our parameters, we can actually separate them into classes remarkably well. So we just need to spend some amount of time tuning them. It's not a perfect separation. So you see, this is a discrete class. This is Z1. This is discrete class. This is Z2. You can see that if you take the one transversal cross-section across Z1, the class separation looks like it's good. Practically, it's not, because we still have a mixture between the different classes, different ground truth labels. So only the diamonds were separated well enough. But other than that, it behaves kind of consistently with the way we expect our autoencoders to behave. We have the disentanglement of the representation within the latent space, so things generally work. Same principle of applying it for the graphene data sets. So this is the example where we apply it for same graphene data. We find the angle encoding. So this was joint rotational autoencoder. We find our latent variables. So notice that they look to be well behaved. So we clearly see the smooth contrast. And we found our class labels. And as you can see that in this case, it actually worked, that we clearly have two different classes. One class associated with the ideal graphene and the second class associated with the defects in graphene. So we can play with increasing the number of latent variables. And again, it's something that's can require some experimentation to see what works for you. Now, this being said, let's have a look at the application of the variational autoencoder for the EELS dataset first. So because this one I haven't shown you, and let's just see how the VIEs actually work for the EELS data. So in the collab on the GitHub, you will find the file which is called VIE EELS that you should be able to run. So this is a summary of the application of the autoencoders for the example of the plasmonic spectra in the nanocube. So the nanocubes were made by the Dille-Milleron group maybe 2 or 3 years ago. So one of my colleagues in Oak Ridge has collected a large set of the hyperspectral plasmonic EELS imaging on them. And basically, we built a notebook that does the full analysis of this data set using the collection of the VIE tools that we have. In principle, I have exactly the same notebooks adapted for the CITS data. So for the tunneling spectroscopy of the grid, for the cathodoluminescence spectra, for the IV spectroscopies and AFM. So basically, at some point, I have adapted it for virtually all hyperspectral imaging modes that we worked with. But this particular example is for EELS, since the school is about the electron microscopy in the first place. So what does it do? So of course, we start with the installation of the Maxim's PyroVed library. And after that, so it will take some time to set up. I should make sure that my runtime is correct. Okay, that's good. Then we import the useful functions. So NumPy, Torch, scikit-image. I will show you why it is necessary. Some function from scikit-learn, some function from matplotlib, and of course the PyroVed. This is our primary library. So after that, we are going to import the EELS dataset. So in this case, this is the data that has been already acquired. It has been cleaned up. So we removed any vestiges of the cosmic ray noise and stuff like that. We normalize it. So basically, this is not the data as it comes from the microscope, but this is the data the way after some amount of cleaning and curation. So as you remember, the first part of our course was dedicated about how do you work with this data and how do you do the instrument-specific cleaning. So we get it from the Dropbox, we load the file, and after that, we will visualize the file. So the way that you visualize the hyperspectral data sets is you simply, so let's see what happens here. So we load our data sets, we create a grid spec object that allows us to visualize it. And after that, we simply visualize the images associated with our data. So what you see here is the collection of the plasmonic structures. So some of them are relatively simple, so just 7 particles kind of stuck together. Some of them are somewhat more complicated. So you see that there is an empty space, there is a single layers, and then there is a kind of multiple layers of the particles. Some of them are kind of a splotch of the particles when you have one layer and then you have a second layer on top of it. Some of them have a change in ordering. So you can see that here you have one sense of orientation of plasmonic particles. This is a different sense of orientation. And here there are 2 particles. This is something weird. So it looks like we are looking it on the side. So pick your example. So why do we choose to look at this type of objects, and why we did pick these particular examples? Because they have a considerable number of factors of variability that we can explore, and we kind of can make hypotheses in real time. For example, I can make a hypothesis that plasmonic properties here are different from plasmonic properties here. Or I can say, look, I'm interested in the collective effects, and particularly the behaviors of the plasmonic responses close to the edges. And this is the example where I have a very sharp edge, and I can sort of explore what happens, what's the difference between here and here. So this is another example when you have a single particle and the edge of the collection of the particles. So in other words, we can choose different scenarios that we want to play with. So let's choose the example number 9 and just load it. Okay, we don't need this one. So then let's define our data object, and let's just look how the data look like. So always a good idea. So in this case, for simplicity, we just work with the data as it is. We can choose the cross-section. So remember that EELS dataset is the 3-dimensional dataset. So 2 dimensions are X, Y. 1 dimension is the energy. So if we want to explore this type of data set, we can choose to look at the cross-section. So here we have chosen the cross-section corresponding to the 200. So 200 is here. So let's see how it looks like if we look at the cross-section corresponding to the 500. So in this case, you can see that we start to see some contrast, so associated with the particles. So let's see what happens if we are in this region when there is a little bit of the shoulder. So this would be about 700. So let's see what we have. And lo and behold, the contrasts have changed. So in principle, it's not a problem to generate images corresponding to any energy, kind of go through them as a video. Of course, 4,000 is too much for this type of representation. So you can see that practically we have widths of these peaks of the order of several hundreds, which means that if we average it somehow by maybe kind of decimate the data sets, we don't expect to lose any energy resolution. And that's what we discussed in one of the first lectures with the averaging. So there is a lot of things that you can do to represent the data. Nonetheless, the most important thing is that we have an idea of how it looks in space, and we have an idea of how it looks in the spectral domain. So the first thing that we do when we explore the new data set is almost invariably a PCA and an NMF. So the reason why these are the great techniques to run is simply because that these are the most simple from the point of view of the data analysis, and they are also linear methods. Linear is good because because you cannot go wrong. So you can get too many components without well-defined physical meaning. That's absolutely true. But you simply will not go wrong in terms of the analysis. It's not going to drop into some form of the false minimum. It's just going to give you the general idea what happens within the data. So the first thing that we do when we do the PCA is of the screen plot, meaning the explained variance is the function of number of components. So you can see that the first several components are important. So something may or may not be happening here. And then after 20 components, we sort of start to have the noise tail. So we can examine these components in the real space. So this is our standard PCA analysis code. So these are the components. You can see that, as we can expect, the first 5 are very clean and show clear variation of the signal. So baseline, first shift, widths, maybe widths. I mean, they're difficult to assign the physical meaning in this particular scenario, but it's intuitively clear how they change the data. And then if we go for more senior components, you see that they are primarily noise dominated. They still have a lot of useful variation, as you can see here, but they mix it with noise. So this is the biggest problem with the PCA type of analysis, is that they allow you to select the most important components, and that would be a good fraction of your signal, but then they take another good fraction of your useful signal and spread it over the multiple noisy components. So we can learn the same type of considerations from the abundance maps. So those are actually great. So you can see here that clearly something is going on, because first of all, if you focus on the particles themselves, you see that they have some contrast variation associated with the particles. What's interesting is that this contrast is absolutely not uniform. You can see that this one shows contrast here and then it drops off. This one sort of shows the maximum in this middle line. This one seems to be that all the particles are the same. This is not random, and this is not a figment of analysis. It is actually the signatures of the emergence of the collective behavior in the plasmonic nanoparticles arrays. And in some sense, this is really cool because we start to see the physics of the essentially photonic behavior. So nanoplasmonic is behavior of the optical wavelengths, optical waves on the length scale below the wavelengths of optical radiation. we basically see how the collective coupling modes emerge from the interaction with the particles. You can also see that we see some cool behaviors from the standalone particle, because in some modes it is not visible, so it is just doesn't show much contrast here. So we can conclude that this component is actually something related to particle interaction. In some modes, it's actually very bright. In some modes, it shows you the dipolar pattern, like plus minus. Here it shows you the sort of like dz square orbital, negative in the center, positive on the outside. Here it is something else. Then, of course, it becomes a little bit more complicated. And you see what I mean when I say that we start to have a mixing between the useful contrast and the instrumental instability, because the noise is clearly associated with the specific scan line. That's how we know that it is some form of the relatively slow instability in the instrumental setup. So out of curiosity, I encourage you to play with the other data sets, because you can sort of follow the same logic of what I see in the geometry of these images and what I'm going to see once I do the PCA analysis. But again, in all cases, the point would be that we are going to have too many components. Now, let's see how long it will take us to run the VAE analysis. So let's start with the standard VAE. So let me run the code so we don't waste time waiting until it converges. Okay, so now this is the part where we train the network. So let's go back to the top of this section and see what is that we have been doing. So first of all, we create our data object. Then we flatten him. So instead of x, y energy, we have one dimension which is combined, x times y, and energy, which kind of makes sense. Then we normalize the data. So, and after we normalize the data, we look at the histogram of the data just to make sure that we get the answer that we want. Now, the reason why we normalize the data and how normalize the data is a very, very important point, because there are many ways we can normalize the data. For example, we can take each ill spectrum and normalize it from 0 to 1, which is what we've done here. So it's not that's one way of doing it. So if we do that, we, strictly speaking, separate the total intensity of the ill signal as a separate variable, and we need to keep track on that variable and look at its spatial variability. And then we'll analyze the shape of the remaining ill spectra. We can also take the maximum of the whole hyperspectral data set, so just one value, and then we can divide each ill spectrum by this value. That's also a very legitimate approach to analyze the data. They have slightly different meaning, because in one case, you analyze only the shape of the ill spectra, but not the intensity. In other case, you will be kind of analyzing the variation and shape jointly with the variation of the intensity. Which analysis you choose depends on what physics do you want to explore. As simple as that. There is no right or wrong answer. There is only a choice that you need to make. And of course, when you write a paper, you basically acknowledge that I did it this way, or I did it this way, and this was my logic. The reason why we share the notebooks as a part of publication of the paper, because basically anyone who reads the paper can can run the analysis differently and see whether there is something in the original analysis workflow that we missed. So anyway, this is the histogram after the normalization. So the reason why we are doing it and what we are looking at is to see that the distribution of the signal is fairly uniform or fairly well behaved. So if we see some kind of gap and then there is one outlier over here, we would know that we definitely need to clean our data more because there is some outlier. VAEs are sort of more or less tolerant to the outlier, but they will severely distort your latent distribution and your latent representation. So garbage in, garbage out. So then we can create our training data. We can look at the examples of the data to sort of see how the spectra behave. So you can see that some of them have one peak, some of them have two peaks, some of them are narrow, some of them are broad. So there is definitely a significant variability in the data. And then we train the autoencoder. So one thing that you will notice is that in all cases, our analysis part looks very simple. So we define the dimensionality of the input signal. We use the invariant VAE model. It has several parameters, including include dimension, so the size of our data. So this is 1D. We specify the number of latent dimensions. We specify the invariances. So in this case, they are none. For one-dimensional data, we can have either none or translation. Basically, translation is very convenient to add when you have a jitter in the data or you have a systematic difference in the position of the peak. Then translation becomes very useful. Then there are several other parameters that are associated with how the VAs work. So we are not going to talk about them because it requires a little bit deeper dive into the VAs. But this is some of the parameters that you can use in order to optimize the convergence. So then you create the trainer object, and then you basically train your network, make a step of trainer using your train loader. So that's it. And then, as usual, you have a statistics which tells you how the algorithm is converging, and then you can visualize the latent space. So lo and behold, what you do in order to visualize the latent distribution is you take your data and encode it using the trained out encoder. So once you take your data set, so its dimensionality is 4,000, same as the number of data points in your spectrum. Once you encode it, you basically create your Z-min, which is your latent vector. And then you can visualize this latent vector, and lo and behold, you can see that your latent manifold is almost, but not quite one dimension. So it's not a straight line, but it's basically one-dimensional object in the two-dimensional space. So what does it tell you? It tells you that after we normalized our data for intensity, we essentially have a single factor of variability or single primary factor of variability in our yield spectrum. So remember that we went through multiple examples for cards or MNIST data sets when I was showing you saying that this manifold is two-dimensional, this manifold is one-dimensional, and in those cases, we could superimpose the ground truth labels and sort of see where things come from. So in this case, we don't have ground truth label, but we know that the manifold is one dimension. So we speculate that there is a single primary factor of variability in our yields data set. If we try to do the PCA, if we try to do the analysis using the PCA, it will be spread over multiple dimensions, but in the VA, it's all kind of together. So we can visualize the learned latent manifold, and we can plot the latent variables. And so what do we see here? We see that in this case, we have the latent variables that look like this. One of them shows the particles. Another basically is associated with the contrast, with the free space. Interestingly, our standalone particle is sort of visible, but it's kind of identifies with the free space. And what's interesting is that we can clearly see that there is some anomalies inside the material. So you see that this point is anomalous and this point is anomalous. That's interesting. So let's go back to our PCA analysis and see if we can detect it here. And the answer is sort of maybe. You can see that this point is darker and it's a little bit different here. But generally, I would say that at least in my case, I would not be able to notice it during the exploratory data analysis. At the same time, the VIE have shown it very clearly. So we don't know what it is, but once we have a red flag that tells us something unusual happens here and something unusual happens here, what we can do is to basically use some form of masking to find out the spot, and we can extract the spectrum from this location, and then we can try to find out what the spectrum is. So that's kind of very straightforward. So again, VIEs don't necessarily tell you the physical meaning of what you're looking at, but they definitely help you to identify the outliers, and then you can choose to go back to the original data set and see what these outliers are. So I'm not going to run the notebook after that because some of the codes may take longer, but you're more than welcome to do so. So the next thing I try to do is to run the VIE assuming that my latent space is three-dimensional. So all I have to do for that is use exactly the same construct, except that I use latent dimension is equal to 3. So again, I train it, then I visualize the latent space, and now I'm actually starting to see something different. So something really interesting. So look what happened here. So I can see that our latent space is almost one-dimensional, but sort of looks like there may be some broadening here and here. We don't know what it is. If I expand the dimensionality of my latent space, you can see that I allow these small factors of variation to be expanded, and you can see that there is definitely some points, some additional factors of variability in the system. They are relatively weak, so there are not that many of them. The majority of my data points are laying on this manifold. So basically, the way that you interpret this data set is that you say that this is a three-dimensional representation. You just look at it from different projections. So from one projection, it's almost a straight line. But from other two projections, you see that we opened up into the plane. So if we do the two-dimensional VIE, we kind of compress into the one. And this is what happens with the latent spaces. So see what happens now. So in this case, you can see that one of these latent factors, so the two latent factors of variation are almost the same, but one of them start to pick up the difference within these particles and the clear difference between this particular particle and everything else. And it required additional space because the number of these points is actually very weak. So again, there are multiple ways how we can work with this data set. For example, we can use some form of label to find these points and see where they're in the latent space, or we can choose these points in the latent space and see where they're in real space. So this is how we go backward and forward between the real space representation and the latent spaces. And of course, we can represent the data in the, so if you have three latent variables, you can represent the data using RGBs and see how the colors behave. So this being said, let's go to the joint autoencoders. So as a reminder, JVIE tries to separate the data in the classes and try to disentangle the representation within each class in a similar manner. So how would we do that? So the loader in this case is the same. This is a fully unsupervised method. So the only thing that changes is that we use a different model. So this becomes JVIE rather than normal VIE. We have the number of dimensions. We have the number of the latent dimensions. So as before, we specify the number of the discrete dimensions, and then everything else is the same: invariances, sampler, and decoder. So the way that we run it is exactly the same. We can configure our training loop in such a way that we get the manifold every 10 iterations. So we see how the process goes. So you can, oops, 1 second. So you can see that we trained it for 10 epochs. We have shown the latent representation for each class. We trained it for another 10 epoch. We showed the latent representations for each class. So we kind of learned how the things go on. We visualized the loss history. So notice an important thing that JVI is kind of unusual in that it very often shows multiple waves on the training history. So normal VIE is usually smooth. JVIE converges, then it stabilizes, then it can converge more. So that's part of the reason why training them can be a little bit tricky. And then what we can do is we can visualize our latent space. So we use our manifold function. So we choose the number of representation and we choose which of the discrete variables we want to show. So we have 3 of them. So we show 3 of them. And then we can encode our data in order to give our mean and prediction. And in this case, you can see that it actually didn't work. So in this case, we trained the joint Y, but it decided that all of our data actually belongs to the same class. So the reason why it didn't work in this case is because the classes are very significantly imbalanced. So there is a very few examples of one class and a lot of examples of the other class. And JVI doesn't work very well in this type of scenarios. There are ways to improve it by using the tuning the information capacity, so how many objects we expect from this class. But we need to kind of get this expectation from somewhere. There are ways how you can do that. So simplest way is to explore things like k-means or clustering first or GMMs and so on and so forth. And basically, you can always get an answer if you somehow balance the VIEs and the clustering. But in this particular case, the JVIE didn't work particularly well. So anyway, we can look at the answers. We don't see anything particularly new. So sometimes things work, sometimes things doesn't work. Now, let's look at how the continuous conditional VIE works. So this is, as I mentioned, this is a very interesting algorithm that allows us to explore the data, assuming that is conditioned on some known factor or factors. And the speculation and all the use cases I have seen for the CVIE is that if you condition on some data, you will remove this factor of variability from analysis. So the problem is that once we deal the yields data, we don't have any natural conditions. So we kind of need to come up with our own. So one way you can work with this type of data is to condition it on the PCA component. So you basically say that one factor of variation on the PCA component, let's see what the CVIE is going to find in all remainder of the data. So this is how it is done. We just take the conditioning vector from our PCA example. Then we look at the dimensionality of our training data and the conditioning vector to make sure that everything in order. We create our train loader object, which we inform by the data and the conditioning vector. So as you can notice, you need to experiment a little bit to make sure that your dimensionality and data formats are right. So the right one, correct one, it should be a torch vector of this size. So then we can look at our data, and this is how the training look like. So we define the invariant model. So we say that this is our input dimension, this is latent dimension, this is the dimension of the conditioning vector. So we choose one, but it can be higher dimension if we can get them from somewhere. Then we train the whole thing. And again, then we look at the data in the latent space. So what you see here is the example of the data after training when we color it by the conditional vector. So you can see that there is no logic in the distribution of the conditional vector in the latent space, as there should be because we took it out. And then we can look at the data representation when we now visualize the factors of variability where the first PCA component has been removed. So in this case, effectively, we have three latent variables. One is our predefined latent variable, which is the conditional vector, and then we explore what is else there in the system. And interestingly enough, we see that our factors of variability has actually changed. So now we pretty much, the contrast associated with the particles become very weak. So compare it to the normal VAE analysis or JVAE, where the primary contrast is between the particles and the background. So once we conditioned on the first PCA component, the first PCA component has the strongest effects from the difference between the particle and the background. So we remove this difference. Once we remove this difference, you can see that now our primary variation between this particle and kind of variation of the contrast. So the last thing that I want to show for the semi-supervised VAEs is the SSVAE. So in this case, the question, however, becomes where do you take the labels? So that takes a little bit of effort, and there are multiple ways how to do that. So the simple way is to, for example, take the PCA components and use some form of the maximum finder in order to find the relevant locations. So if you look at the structure of this code, I basically take my input data, I take the PCA components, and then I use the maximum filter in the and finding peaks in the scikit image in order to find the relevant positions. So I use the first PCA component maxima, I use the second PCA component maxima, and the second PCA component minima. And this allows me to find, this is one reference point, this is second set of reference point, this is the third reference point. So one class has one example, this red dot. Second class have multiple examples, which are these red dots. And the third class have two examples, which is here and here. So notice that this is kind of very ad hoc, and then there are multiple ways how this type of analysis can be done. So for example, I can do it manually. I can click here, here, and here and tell this is my first class, click here, here, and here and say this is second class, click here and here and say that this is third class. So, and of course I can specify any number of classes that I want. The key thing, however, is that once I specify the classes manually, I want to find, to take all the other objects and identify them in terms of these classes. So the way you do that is by creating your label stack. Then you basically create the labels 0, 1, and 2. So just a kind of labeling convention. Okay, and here, this is, then we train our, okay, wait, sorry, 1 second. So then we train our, we create the data loader. So in this case, it is more complicated because we provide the loader for the unsupervised part of the data, and we provide the loader for the supervised part of the data. So the first is all data set, second is the one with the labels, and after that we train our autoencoder. So we provide the number of dimension of the signal, we provide the latent dimensionality, we provide the number of classes. And by the way, one important thing, notice that we have X sup and Y sup twice. So the reason for that is that semi-supervised VAE is the semi-supervised method, which basically means that sometimes we want to have a validation data set. So in this case, we don't do that, but in principle, it's possible. So then we train it. Once we train it, our output would be the manifold for all the classes, and our output would be the predicted classes for all the data sets. Again, you can see that in this case, all the predicted classes are class 1. So what happened? Basically, this is the problem with the selection of the labels. If I choose the labels like this, then there is not that much difference between the average spectrum and these locations and this spectrum and this spectrum. So it is possible to make this data set to converge to something to provide the separation, but again, this is the case where you want to experiment. And the final thing that we can do here is remember the principle that if you run the machine learning algorithm, it is always a good idea to compare it to the simple algorithm like supervised regression. So, and just for fun, this is what the supervised regression will do here if we try to train it on the same algorithms. So again, it shows us something interesting and allows some sort of differentiation of the particle behavior. And actually, from the point of view of the analysis, in this case, for this particular data set, supervised regression gives pretty good answers. So not always the case, but in this case. Now, so this is how we make the this VIEs work for the spectral data. So let me show you how it will work for the imaging data for the examples of the cards. So the codes in this case would be very similar. So let me show you the example for the cards dataset. So it should be also on the GitHub. So the installations are exactly the same. So we installed the PyroVed and we install Cornea. PyroVed contains the VIEs. Cornea contains the transformation functions. We use the standard imports as before, and we use create the helper function that creates the data sets with the different orientations and degrees of disorder. So you already have seen this example last week. So we download a cards object. We create 4 data sets that vary in terms of the angle, translation, and share. We visualize this data set. We create our train loaders that give us access to the different degrees of the disorder. And then we train our conditional rotational invariant autoencoder for the first example. So what's the difference? So pretty much the only difference is that we have a different input dimensionality of the data. So now it is 48 by 48, so it's our card image. Our model in this case kind of has a little bit larger number of variants. So we have the input dimension. This is dimension of the data. We have a latent dimension, so how many factors of variability we want to find. We have our conditional vector, and then we introduce the rotational invariances. So when we train it, we get our output, and we also save the data set. And then we train it 4 times. So this is going to be fairly slow, so I'm not going to show that. Then if we visualize the results, oops, in this case, the results didn't save. Okay, sorry about it. So let's see how long it was going. Okay, I need to run it and see how it behaves. So that's unusual. Okay, I know what goes on. Okay, give me 1 second. Okay. Yeah, unfortunately, I didn't save the analysis for that one. So I will have to rerun it and put it on the put it on the GitHub. Okay, let's look at the joint one in the meanwhile. So let me switch to the right window. Here we go. So this is the example of the notebook for the joint autoencoder. So again, the beginning of it is going to be exactly the same. So our creation of the augmented data set. This is the training, and this is how you, so this is the training part. So you initialize your model with a certain size and dimensionality. Then you do the fit, and then you visualize the results. So this is how the original data looks like. This is how the latent distributions will look like. So in this case, this is the example with the fairly small disorder. So you can see that in this case, we were able to separate the cards into the different latent spaces remarkably well. So this is our continuous latent variable. This is our discrete latent variable. You can see that in this case, the 4 suits are separated perfectly. And if we look at the individual latent spaces for each classes, one is very clearly all hearts, another is all clubs, another is all diamonds, and the third one is all pikes. So it worked exceptionally well. So if we look at the latent distributions, so you can see that they are also exceptionally well defined. So we actually separated our cards remarkably well. So the labels are clear. So if we look at the ground truth, you see that they all mixed, which makes sense because in this case, so this is the normal VIE, this is the joint VIE. So in this case, the labels correspond to different latent variables, which means that within the latent spaces for each variable, there is no variability anymore. And we were even able to discover the angles properly. So this happens if our angle distribution is relatively weak. So if we start to add a strong shear, the answers are going to be different. So in this case, if the disorder is strong, our separation is not so clean anymore. So you can see that we start to see the mixed objects in the same discrete latent space. And if we look at the continuous latent spaces, you can see that they are clearly defined, separated between the clubs, pikes, and hearts. And so in this case, the diamonds got a latent space all for themselves. The third latent space is again a mixture. So in this case, we actually separated them in the latent space, but unfortunately, there is still mixing between the classes. And you can see that this is what happens if we look at the labels, and this is what happens if we look at the shears within the data set. So, and the angles in this case are not particularly well defined. So if we have high rotation and low shear, then this is what is going to happen. So notice that in this case, our latent spaces are actually well behaved because this is a rotationally invariant autoencoder. So basically, despite the fact that our rotations are changing quite a lot, we were able to assign the right class for each object. So almost right class. There is still a small difference between the pikes and cards. So, and again, we can visualize the latent labels and the shears inside the latent space. So finally, the angles in this case, we were able to find the right angle locally. So along this line, but not globally. So there is a jump between the different type of objects corresponding to this imperfection in the latent spaces. And finally, you can see that there is a, if we try to make the rotation and the shear strong, in this case, things didn't work out particularly well. So you can see that if we look at the latent spaces, they contain objects from multiple classes. For example, from this type of hand, this type of hand, and this type of hand, and you can see that they kind of separated across the one latent variable, but here they're oriented to the left, here they're oriented to the right, and these ones are in between. So in some sense, our joint out encoder was able to separate the data set. However, it's imperfect. So if we try to squeeze a high dimensional manifold in the low dimensional space, sometimes it is successful, so we can kind of flatten it out and get the right answer. But in some cases, it's rather imperfect, and the separation is good locally, but not globally. And again, this is the example of the labels, and this is the examples of the shear. So this should be shear, not the label. So this being said, I will upload the rerun notebooks on the GitHub, so you can look at the answers. And I will post the notebooks which analyze the graphene data. So do you have any questions that that we can discuss? So if there are no questions, then let's call it a day for today. So finish slightly earlier. And on Friday, we will have a fairly short lecture talking about the variational encoders, decoders, meaning how you build the relationship between the structure and yields and what can you learn in the progress. So see you on Friday.